Hi everyone. Today we're going to explore how changes in dimensions affect area and perimeter. So tweaking just one dimension in a figure can make an important difference in its perimeter and area. In this lesson, we will look at some geometric figures and explore how the individual dimension affect the overall perimeter and area and how small changes at some points can make a huge difference in the results. First, let's review some concepts such as area and perimeter. Let's start with dimensions. Dimension is one of the measurable characteristics that determine the shape of the figure. It could be the length of one of the sides of a polygon or the radius of a circle. It could be the height of a triangle or of a three-dimensional figure such as a cube or a pyramid. Whether it is length, width, height, or something else, a dimension provides a good starting point for examining other properties of a figure. Now, let's define the perimeter. Perimeter of a polygon is the sum of the length of the sides of the polygon. Some shapes have special formulas for perimeter, but all are derived from the basic definition of a perimeter. Now let's define the area. Area of a figure is the measure of how large its surface is. Area is given in square units, such as square inches or square miles, and it's usually determined by calculation that involve multiplying the figure's dimension. Um, this table shows formulas for perimeter, circumference, and area of some geometric figures. For example, the area of a triangle is 1/2 base times height. The area of a square is the side square, and the perimeter is 4 times the side. The area of a rectangle is length times width, and its perimeter is 2 times the length time plus 2 times the width. And the area of a circle is pi times radius square, and its circumference is 2 times pi times the radius. Now let's review the concept of similarity. Similar polygons have the same shape but not necessarily the same size. So two polygons are similar if and only if their corresponding angles are congruent and the corresponding sides length are proportional. Um, Here we have an example of two similar polygons, ABCD and WXYZ. So we can see that angle A is congruent to angle W, angle B is congruent to angle X, angle C is congruent to angle Y, and angle D is congruent to angle Z. We also have the side AB over WX equal to BC over XY, and that equal to DC divided by ZY, and that equal to dA divided by ZW, and that is equal to 3 over 1. And 3 over 1 is actually the scale factor, because in two similar geometric figures, the ratio of their corresponding sides is called the scale factor. Uh, it is important to notice two things about the scale factor. The scale factor for the first figure to the second is always the reciprocal of the scale factor from the second figure to the first. In the previous example, we have the scale factor of ABCD to WXYZ is 3 over 1, and if we want to find the scale factor of WXYZ, to ABCD, so that would be 1 over 3. And we also should know that if you begin with the smaller figure, your scale factor will be less than 1. And if you begin with the larger figure, your scale factor will be greater than 1. Now we can see that the scale factor of ABCD to WXYZ is 3 over 1 and is greater than 1 because ABCD is the larger polygon, and the scale factor of WXYZ to ABCD is 1 over 3, and then you can see that that is less than 1 because WXYZ is the smaller polygon. Now let's see what's going to happen to the perimeter when the dimensions start changing. In similar polygons, the ratio of inner to corresponding length is proportional to the scale factor between them. This leads to the following theorem about the perimeters of two similar polygons. So the theorem says if two polygons are similar, then their perimeters are proportional to the scale factor between them. For example, if ABCD is similar to JKLM, then the perimeter of ABCD divided by the perimeter of JKLM is equal to AB divided by JK and equal to BC divided by KL and equal to CD divided by LM and equal to DA divided by MJ. For instance, let's sketch a square with a side length of S, and then if I sketch a similar square with side length of 2S, then the scale factor of the larger square to the smaller square is 2S divided by S, which is equal to 2 over 1. Now we have the perimeter of the smaller square is 4 times S, and the perimeter of the larger square is 8S, which is 4 times 2S, so that will give us 8S. Now we can see that the increase in the perimeter is an increase of 4S, or we can say that is doubled, and the scale factor is 2, so that explains the relationship between the scale factor and the change in the perimeter. Now let's do an example of using a scale factor to find the perimeter. So if ABCDE is similar to PQRST, so these are the two similar polygons, then find the scale factor of ABCD to PQRST and the perimeter of each polygon. So let's start with the scale factor of ABCDE to PQRST. Since we have these two polygons are similar, so then we know that the scale factor is the ratio of two corresponding sides. So let's do, for example, CD and RS. So these are the corresponding sides. So we have CD. The length of CD is 4 and the length of RS is 3. So that means that the scale factor is going to be 4 over 3. Now, since the side BC is congruent to the side AB and the side AE is congruent to the side CD, then the perimeter of ABCD is 8 plus 8 plus 4 plus 6 plus 4, which is 30. Now we have the scale factor of ABCDE to Q PQRST is 4/3, and we have the perimeter of ABCDE is 30. Now let's use this information to find the perimeter of PQRST. So from the previous theorem, we have the perimeter of ABCDE divided by the perimeter of PQRST equal to the scale factor 4 over 3. Now let X represent the perimeter of PQRST. By doing the substitution, we get 30 divided by X equal to 4 over 3. We do cross multiply, then we get 30 times 3 equal to 4 times X, and that will give us the value of 22.5 for X. So since X represents the perimeter of PQRST, then the perimeter is 22.5. Now let's explore how changes in dimensions affect area. So we have already learned that if two polygons are similar, then their perimeters are proportional to the scale factor between them. The area of two similar polygons share a different relationship. Here we have two similar figures, rectangle A and the rectangle B. So we have the perimeter of figure B is 9k plus 5k plus 9k plus 5k, which is 28k, and the perimeter of rectangle A is 9 plus 9 plus 5 plus 5, which is 28. So then the ratio of the perimeter of figure or rectangle B to rectangle A is 28k over 28, which can be simplified to k. So we know that k in this case is the scale factor. Now what if we do the same thing for the area? So we have the area of rectangle B is 9k times 5k, which is 45k squared, and the area of rectangle A is 9 times 5, which is 45. So then the ratio of the area of rectangle B to the area of rectangle A is 45k squared divided by 45, which can be simplified to k squared. And we know that k is the scale factor. Now we can say if two polygons are similar, then their areas are proportional to the square of the scale factor between them. For example, if ABCD is similar to FGHJ, then the area of FGHJ divided by the area of ABCD equal to FG divided by AB, and everything is squared. Now let's do an example of using scale factor to find the area of similar polygons. So if the triangle JKL is similar to the triangle PQR, and the area of JKL is 30 square inches, then find the area of triangle PQR. So we know that the scale factor between the triangle PQR and JKL is 15 over 12, which can be simplified to 5 over 4. And according to the previous theorem, then the ratio of their areas is 5 over 4 squared. Now if we write the proportion, then we get the area of the triangle PQR divided by the area of triangle JKL is equal to 5 over 4 squared. And since we know that the area of the triangle JKL is 30 square inches, and 5 over 4 square is equal to 25 over 16, then we can plug in these values. So we get the area of triangle PQR divided by 30 equal to 25 over 16. If we multiply each side by 30, then we get the area of triangle PQR is equal to 25 over 16 times 30. So if we simplify, then we'll get the area of triangle PQR equal to 46.875. So the area of triangle PQR is about 46.9 square inches. Now let's summarize what we have learned today. So the change in dimensions can be done by multiplying all the dimensions by x, and x here is the scale factor. Now the perimeter or the circumference changes by the factor of x, and the area changes by factor of x squared.